Hi, welcome to the Random Walk and Bayes Theorem, Part 2. This is the second part in a three-part series where we look at an object undergoing a random walk. In Part 1, we looked at a four-step random walk that started at x equals plus 2 or x equals minus 2 with equal probability. After the four steps, the object was at x equals plus 2. We asked for the probabilities, given that the object ended up at x equals plus 2, for the object to have started at each of the two initial possibilities, x equals plus 2 and x equals minus 2. Here in Part 2, we'll see how we can relate this result to an important concept in probability called Bayes' theorem. We'll also see how our result depended upon something called our prior probabilities for the object to have started its walk at x equals plus 2 or x equals minus 2. We'll then change these prior probabilities and see how it affects our result. This video leans heavily on Part 1, so you should watch that video before proceeding here. While it might be useful to have some knowledge of Bayes' theorem for this video, it won't be assumed. However, you may be interested in looking at some of the videos in the Bayesian playlist either before or after watching this video. Okay, let's get started. First, let's briefly recap what we saw in Part 1. We had an object undergo a four-step random walk. It started the random walk at either x equals plus 2 or x equals minus 2, with equal probability. It takes four steps. Each step is one unit, either to the right or to the left, with equal probability. After four steps, it was at x equals plus 2. We wanted the probability, given that it ended up at x equals plus 2, that it started at x equals plus 2. And we wanted the probability, given that it ended up at x equals plus 2, that it started at x equals minus 2. In order to answer this question, we can look at all of the different ways the procedure can play out, along with their probabilities. Then we can look at all of the cases where the object ended up at x equals plus 2. Out of these cases, we can see what fraction originated at x equals minus 2 and what fraction originated at x equals plus 2. Okay, so the first step of the procedure is that we start the object at either x equals plus 2 or x equals minus 2 with equal probability. So the probability that it starts at x equals plus 2 and the probability that it starts at x equals minus 2 are both 1/2. Okay, then the object will take four steps. Each step is either to the right or to the left with equal probability. So the object will take one of 2 to the 4th, that's 16, paths, all with equal probability. We saw that if the object is started at x equals minus 2, there is one path that leads to it ending up at x equals plus 2. So if the object starts at x equals minus 2, the probability of it ending up at x equals plus 2 is 1 divided by 16. And if you want to compare that with the plot at the right, it's useful to know that 1/16 is equal to 0.0625. And if the object starts at x equals plus 2, there are 6 paths that lead to it ending at x equals plus 2. So if the object starts at x equals plus 2, the probability that it ends up at x equals plus 2 is 6/16, which is equal to 0.375, which you can see on the plot. So the probability that the object starts at x equals minus 2 and ends at x equals plus 2 is equal to 1/2 times 1/16. Here the 1/2 is the probability to start at x equals minus 2, and 1/16 is the probability to end up at x equals plus 2 if it started at x equals minus 2. Now that product is equal to 1/32 and is represented by the red bar shown at x equals 2. So if you'd like to compare with the plot, 1/32 is equal to 0.03125. And similarly, the probability that the object starts at x equals plus 2 and ends at x equals plus 2 is 1/2 times 6/16, which equals 6/32. This is equal to 0.1875 and is represented by the green bar located at x equals 2 on the plot. So the total probability that the object ends up at x equals plus 2 is the sum of these. So 1/32 plus 6/32, which equals 7/32. And numerically, that's equal to 0.21875. Now, given the object ended up at x equals plus 2, the probability it started at x equals minus 2 is 1/32 divided by 7/32, which equals 1/7. So here we've divided the red by the red plus the green. And the probability it started at x equals plus 2 is 6/32 divided by 7/32, which equals 6/7. So that's the green divided by the sum of the red and green. Okay, so now let's write this down a bit more formally. We calculated two quantities. The first is the probability, given that the object ended up at x equals plus 2, that it started at x equals plus 2. We write this as P of start at plus 2 given end at plus 2. The other thing that we calculated was the probability, given that the object ended up at x equals plus 2, that it started at x equals minus 2. So we'll write this as P of start at minus 2, given that it ended at plus 2. Now, the probability that it starts at plus 2, given that it ends at plus 2, and the probability that it starts at minus 2, given that it ends at plus 2, are conditional probabilities. Let's see how we calculated them by looking back at our plots. We'll focus on the probability that the object started at plus 2, given that it ended at plus 2. To calculate the probability that the object starts at plus 2, given that it ends at plus 2, we did the following. We said the probability that it started at plus 2, given that it ended at plus 2, was equal to the probability that it would start at plus 2 and end at plus 2, divided by the probability that it would end at plus 2. To see this, let's look back at the plot. Here, the probability for the object to start at +2 and end at +2 was given by the green part of the bar located at x equals +2. The probability for the object to end at +2 is given by the total, the green plus the red, of the bar located at x equals +2. So at x equals +2, we divided the green by the green plus the red. In doing so, we calculated the right-hand side of the relation we just saw. So we calculated the probability to start at +2 and end at +2 divided by the probability to end at +2. Now let's look at the factor in the numerator of the right-hand side. So the factor, the probability to start at +2 and end at +2. To get the probability to start at +2 and end at +2, we multiplied two factors. These factors were 1, the probability for the object to start at x equals +2, and 2, the probability for the object to end up at x equals +2, given that it started at x equals +2. Let's look at each of these factors. We'll start with 1. So the first factor was the probability for the object to start at x equals +2. We'll call this factor P of start at +2. It was equally likely for the object to start at x equals +2 or for the object to start at x equals -2. So this is 1/2. So we have P of start at +2 equals 1/2. The second factor was the probability for the object to end up at x equals +2, given that it started at x equals +2. This is a conditional probability. We will write it as P of end at +2, given that it started at +2. To get it, we look at our plot of ending point probabilities for the case that the object started at x equals +2. We saw that if the object starts at x equals +2, the probability that it ends up at x equals +2 is 6/16. So P of end at +2, given that it started at +2, is equal to 6/16. And we should note that our previous plot can now be relabeled as P of end at x, given that it started at +2. Okay, so we had that the probability for the object to start at +2 and end at +2 is equal to the probability to start at +2 times the probability to end at +2, given that it started at +2. We can use this to rewrite our previous relation. Okay, so before we had that the probability that it started at +2, given that it ended at +2, was equal to the probability that the object would start at +2 and end at +2 divided by the probability to end at +2. Using our new expression, which is that the probability to start at +2 and end at +2 equals the probability to start at +2 times the probability to end at +2, given that it started at +2, we can write this as the following. We can write P of start at +2, given that it ended at +2, is equal to the probability that it would end at +2, given that it started at +2, times the probability to start at plus 2 divided by the probability to end at plus 2. Now, while it may not be obvious, here we have used something called Bayes' theorem. Bayes' theorem is written as the following. P of A given B is equal to P of B given A times P of A divided by P of B. Here, P of A is the probability of A, and P of A given B is a conditional probability, the probability of A given B. So let's evaluate Bayes' theorem for A equals start at plus 2 and B equals end at plus 2. Bayes' theorem gives us that the probability that the object started at plus 2, given that it ended at plus 2, is equal to the probability to end at plus 2 if the object starts at plus 2, times the probability to start at plus 2 divided by the probability to end at plus 2. But this is the same equation we just wrote down. Okay, so we saw before that the probability to end at plus 2, given that it starts at plus 2, is equal to 6/16. The probability to start at plus 2 is equal to 1/2, and the probability to end at plus 2 is equal to 7/32. If we plug these numbers in to Bayes' theorem, we get that the probability that the object started at plus 2, given that it ended at plus 2, is equal to 6/16 times 1/2 divided by 7/32. This equals 6/7 and is the same answer as we got before. Note that our calculated probability depends on the initial probability, also called our prior probability, to start at x equals plus 2, which we write as P of start at plus 2. We would have gotten different results if, for example, I used a weighted coin instead of a fair coin to decide the starting point for the object. Let's briefly see how that would have worked out. Let's repeat our procedure, but this time the object starts at x equals plus 2 with probability 1/4, and at x equals minus 2 with probability 3/4. So this time P of start at plus 2 equals 1/4 and P of start at minus 2 equals 3/4. Again, after 4 steps, the object ends at x equals plus 2. And we want to get the probability that the object started at plus 2, given that it ended at plus 2, and the probability that it started at minus 2, given that it ended at plus 2. Just like before. Okay, first let's get the probability that the object starts at plus 2 and ends at plus 2, and the probability that it starts at minus 2 and ends at plus 2. We'll start with the probability that the object starts at plus 2 and ends at plus 2. So the probability that the object starts at plus 2 and ends at plus 2 is equal to the probability that it starts at plus 2 times the probability that it ends at plus 2, given that it starts at plus 2. So this is equal to 1/4, so that's our new value for P of start at plus 2, times 6/16, which is the same value we had before for the probability to end at plus 2 if the object started at plus 2. That product is equal to 3/32. And now let's get the probability that the object starts at minus 2, and ends at +2. So the probability that the object starts at -2 and ends at +2 is equal to the probability that it starts at -2, which is 3/4, times the probability that it ends at +2 given that it starts at -2. That's 1/16, which we've seen before. So that product is equal to 3/64. Now, as the object must start at x equals +2 or x equals -2, we can add these two results to get the total probability that the object ends up at x equals +2. So the probability to end up at x equals +2 is equal to the probability to start at +2 and end at +2 plus the probability to start at -2 and end at +2. So that's 3/32 plus 3/64, which is equal to 9/64. Let's see these results on a plot. Okay, so the probability to start at -2 and end at +2 is equal to 3/64. So this is shown in red in the bar at x equals 2. The probability to start at +2 and end at +2 is equal to 3/32. That's shown in green. And the total probability to end at +2 is equal to their sum. So that's 9/64. Now note that over the entire plot there is much more red than green. This is because the probability to start at x equals -2, which is 3/4, is now larger than the probability to start at x equals +2, which is 1/4. Okay, so the probability that the object started at x equals -2, given that it ended at +2, is equal to 3/64 divided by 9/64. So this is the red divided by the sum of the red and green, and that's equal to 1/3. The probability that the object started at +2, given that it ended at +2, is equal to 3/32 divided by 9/64. So this is the green divided by the sum of red and green, and that's equal to 2/3. Do we get those same results when we use Bayes' theorem? From before, the probability that the object started at +2, given that it ended at +2, is equal to the probability that the object would end at +2 if it starts at +2, times the probability that it would start at +2 divided by the probability that it would end at +2. So plugging in our new numbers, we get 6/16 times 1/4 divided by 9/64, and that's equal to 2/3. And that's the same result as we just got. Now, it is important to note that two terms in our expression changed compared to our previous example. So we changed the probability for the object to start at +2 from 1/2 with the fair coin to 1/4 with the weighted coin. But this also changed the overall probability for the object to end up at x equals +2. So the term in the denominator, p of end at +2. Okay, let's also get the probability that the object started at x equals -2 given that it ended at x equals +2, which equals the probability that it would end at +2 given that it started at x equals -2 times the probability to start at -2 divided by the probability to end at +2. Again, plugging in our new numbers, that's 1/16 times 3/4 divided by 9/64, which is 1/3, and again is the same as the number that we just saw. Okay, so let's summarize. In this video, we saw how to relate our random walk results from part 1 to Bayes' theorem. We also saw how our prior probabilities for the object's starting location came into the calculation. In part 3, we'll look at a specific set of prior probabilities, the case where there are a range of possible starting locations, all with the same prior probability. Part 3 will be a good warm-up exercise if you decide to watch How to Interpret a Scientific Measurement with Gaussian Error Bars, or the other videos in the playlist Minicourse on Error Bars, Measurements, and Decision Analysis, available on this channel.